Greetings everyone, I'm excited to present DigiByte flavored UTXO specifications. This presentation is derived from the UTXO Alliance UTXO Handbook, specifically covering the ingredients for a blockchain and general UTXO specifications. Authors, contributors, and anyone familiar with the handbook will recognize the outline of this presentation with a pinch of DigiByte flavor. During this presentation I will be discussing cryptographic primitives, transactions on the network, whole transaction graph plus UTXO set, blocks on the network, features of the chain. Now that we know what will be covered, let's get started. In the DigiByte blockchain, cryptographic primitives are essential for maintaining the security and integrity of the network. Two key components are hash functions and digital signatures. Hash functions create a secure and tamper-proof chain of blocks, linking each block to its predecessor through an ongoing chain of hash-based proof of work. This ensures that any attempt to alter a transaction would require redoing the proof of work for that block and all subsequent blocks, making tampering computationally impractical. Digital signatures using the elliptic curve digital signature algorithm, or ECDSA, provide cryptographic proof of ownership and authorization. This algorithm ensures that each transaction is securely signed by the sender using their private key, and the signature can be verified by anyone using the sender's public key. This guarantees that the transaction was indeed authorized by the rightful owner, preventing unauthorized spending and ensuring that transactions are legitimate and verifiable. These cryptographic techniques are fundamental to maintaining the security and integrity of the DigiByte network. Now let's dive into how transactions work on the DigiByte network. Transactions are the fundamental units of the DigiByte network. Here are some key points. Inputs. Inputs are references to previous transactions' outputs that are being spent in the current transaction. Each input includes a reference to the previous transaction and a cryptographic signature that proves ownership. Outputs. Outputs specify the new ownership of the digibytes being transferred. Each output includes an amount and a cryptographic key or public key of the recipient. Change. If the total value of the inputs exceeds the amount being sent, the difference is returned to the sender as change through an additional output. Inputs and outputs are crucial components of transactions on the DigiByte network. Next, let's explore the whole transaction graph and the UTXO set. The whole transaction graph outlines how transactions are linked together in a chain. Each transaction references previous transactions' outputs as inputs, creating a graph of transactions. This graph ensures that all transactions are traceable and verifiable, preventing double spending. The concept of unspent transaction outputs, or UTXOs, is central to DigiByte's operation. Each transaction output can be spent only once, and the set of all unspent outputs, known as the UTXO set, is maintained by the network. This set is used to verify the validity of new transactions by ensuring that the inputs have not already been spent. These mechanisms are crucial for maintaining the integrity and security of the DigiByte network. Wallets in the DigiByte network manage the user's UTXOs. They generate and store pairs of public and private keys, sign transactions using the private key, and verify transactions using the public key. Wallets also track which outputs are available for spending and use them as inputs for new transactions. The ledger in the DigiByte network is a public, distributed, and tamper-proof record of all transactions. It is maintained by a network of nodes ensuring transparency and decentralization. The ledger's integrity is secured through cryptographic hash functions and proof of work, making it resistant to tampering. The concept of conservation law in DigiByte addresses mechanisms that prevent double spending and ensure the integrity of the transaction ledger. The network maintains a consistent and tamper-proof ledger using cryptographic proof of work and a distributed timestamp server. The sum of all inputs must equal the sum of all outputs. Now let's dive into blocks on the network. In DigiByte, blocks are a fundamental part of the network structure. Each block contains a list of transactions, a timestamp, a reference to the previous block, and a proof of work. This structure ensures that blocks are linked together in a chain, forming the blockchain. Block headers play a crucial role in maintaining the integrity of the blockchain. Each block header includes several important pieces of information: version, which indicates the version of the DigiByte protocol; previous block hash, a reference to the hash of the previous block, ensuring the chain's integrity. Merkle root, the root of the Merkle tree, summarizing all transactions in the block. Timestamp, the current time when the block was created. Difficulty target, the target threshold for the proof of work. And nonce, a counter used for the proof of work algorithm. The block header includes the proof of work, a computational puzzle that miners must solve to add a new block to the blockchain. This ensures the security and immutability of the blockchain. Blocks are added to the network at an average interval of about 15 seconds. The difficulty of the proof of work puzzles adjusts in real time as each block is mined. This process secures the network by making it computationally difficult to alter any part of the blockchain. A special type of transaction included in each block is the Coinbase transaction. This transaction is the first in a block and is used to reward the miner who successfully mined the block. The reward consists of newly created DigiBytes, known as the block subsidy, and any transaction fees from the transactions included in the block. Unlike regular transactions, the Coinbase transaction does not have any inputs. Instead, it creates new DigiBytes, introducing them into circulation. The Coinbase transaction can include arbitrary data in its input field, often used by miners to include extra information, such as a message or the mining pool's name. This transaction is a crucial part of DigiByte's incentive mechanism, encouraging miners to participate in securing the network by providing them with a financial reward. These points highlight the importance of the Coinbase transaction in maintaining the DigiByte network's security and incentivizing miners. Next, let's explore blocks on the chain. The concept of the Genesis block is fundamental to understanding the DigiByte blockchain. The Genesis block was mined on January 10, 2014, marking the beginning of the DigiByte blockchain. In DigiByte, the longest chain of blocks is considered the valid chain. This means that the chain with the most accumulated proof of work is recognized as the correct version of the blockchain. The network relies on nodes to follow this longest chain, which represents the most computational work. The consensus mechanism in DigiByte is based on proof of work. Miners solve complex mathematical problems to add new blocks to the blockchain. This process ensures that the majority of computational power is controlled by honest nodes. The longest chain rule ensures that any attempt to alter the blockchain would require redoing the proof of work for that block and all subsequent blocks, making it computationally impractical for an attacker to succeed. Decentralized consensus is a key feature of the DigiByte network. The consensus mechanism allows the network to operate without a central authority. Nodes independently verify transactions and blocks, and the longest chain serves as a decentralized consensus on the state of the blockchain. The security of this consensus mechanism is such that an attacker would need to control a significant percentage of one algorithm and a speculative 11 to 35% of each remaining algorithm's computational power to alter the blockchain, making it highly secure against attacks. The state of the DigiByte network is distributed in nature. This ensures that the system remains decentralized and resistant to censorship. The network is peer-to-peer, meaning that nodes communicate directly with each other. Transactions are broadcast on a best-effort basis, and nodes can leave and rejoin the network at will, accepting the longest proof of work chain as proof of what happened while they were gone. The consensus mechanism ensures that all nodes agree on the state of the blockchain. The network security relies on the majority of computational power being controlled by honest nodes. As long as this condition is met, the network remains secure, and the longest and heaviest chain will always represent the valid state of the blockchain. These principles ensure that the DigiByte network remains secure, decentralized, and resilient. In summary, DigiByte's robust security and efficiency are built on a foundation of advanced cryptographic primitives, including hash functions and digital signatures. These elements ensure the integrity and authenticity of transactions on the DigiByte network. DigiByte utilizes the UTXO model to manage transactions, maintaining a comprehensive transaction graph and UTXO set. This model allows for efficient tracking of funds and ensures that all transactions are accurately recorded and verified. Blocks on the DigiByte network serve as containers for transactions, forming the backbone of the blockchain. Each block includes a header with crucial information and a list of transactions, ensuring transparency and security. The chain of blocks represents DigiByte's entire transaction history, maintained through the longest and heaviest chain rule, which prioritizes the most secure and proof-of-work accumulated chain. By leveraging these techniques, DigiByte offers a secure, efficient, and transparent blockchain solution, making it a reliable choice for digital transactions and decentralized applications. This concludes the presentation. Are there any questions?